Hey guys, my name is Mason Oleson, and I'm in Dr. Delacourt's Physics 106 class. Today we are going to be learning about the applications of photon momentum. So first off, we probably have a couple questions that need to be answered, and the first one is, what are photons? And of course, our 106 class has already learned this, but photons are little massless particles or packets of energy that can also act like a wave. And if you look to the right, we have the electromagnetic spectrum, which, as you can see on the left, you have a very low wavelength, and on the right side, you have a very large wavelength, going from gamma rays to the visible light, which is actually a really small portion of the electromagnetic spectrum, to radio waves and infrared waves that are over on the right side. And something that we also know is as the wavelength decreases, our frequency increases. And as the frequency of a wave increases, so does the energy. So, what is momentum? Well, typically, momentum is expressed by the equation P equals mv, where P is momentum, m is the mass of an object, and v is the velocity that it's traveling at. The momentum equation can only describe momentum in relation to mass, though. Can quantities without mass have momentum, though? If so, how are photons and momentum connected? That's a question we're going to be answering throughout our presentation today. What is photon momentum? Well, photon momentum can be expressed through the equation P equals h over lambda, measured in kilogram meters per second. H is known as Planck's constant, which is 6.626 times 10 to the negative 34 kilogram meters squared per second. And lambda can be defined as the wavelength of a given photon of light measured in meters. Since photons are massless particles of energy, the original equation, P equals mv, can't be used to express the momentum of photons, which is why we have the photon momentum equation listed above. It was actually derived from the photon energy equation, where E, or energy, equals h times f. H is Planck's constant, and f is the frequency of the wave. How can a massless photon carry momentum? An example or an application that we can see in everyday life, or at least in the science aspect of life, is through solar sails. And solar sails are an example of photon momentum just because solar sails work by capturing the energy that light particles have as they bounce off of a very reflective surface. And each light particle, as it's hitting that reflective surface, it actually has momentum. And as it strikes that reflective surface, a little bit of momentum is actually imparted on the reflective sheet, just like a collision of two billiards balls or two cars that crash into each other, just like we've learned in earlier physics classes. As you see in the lower image here, we have a solar sail over to the left, which is what it would look like if it were in space. And over on the right, that's actually a force diagram. And you have the solar sail, which is the reflective film. You have the sunlight, which is just those photons, which are going to be hitting off of that reflective film. And much like we know, the degree that it comes in, the photons come in at, it's going to reflect at that same angle. So that's why you have those two thetas, I and R. It's because one is the reflection angle. And as it comes in, a little bit of energy is going to be transferred to the reflective film, which is also why we end up with a net force that's going to be in the other direction, the direction that the photons are originally traveling in. So how do solar sails work? Well, much like a normal sail works by air blowing against the large sheet, A solar sail works by photons reflecting off of a large reflective sheet. Much like we've learned in our class with reflection and refraction, when a photon reflects off of a surface, a little bit of energy is imparted on that reflective surface, which is why the photons reflect with a little bit less energy each time they reflect off of an object. While the amount of energy transferred from the sun to a solar sail might be a really small amount of energy, over time, the constant added energy can make a big difference, and you can have a solar sail that's traveling at extremely high speeds. Now that we know exactly how solar sails work and how photon momentum works as a principle, how can we use this to benefit society, or how can we use this to further science? Well, what we know is the energy in the form of photons from the sun is actually being dispensed regardless of if we use them or not. But we can channel these photons in the form of momentum when we use solar sails. And when we make those photons reflect off of objects, we're going to be using that energy. And we can create extremely efficient satellites that actually don't need as much non-renewable energy to get them moving. And this can actually benefit society and science because we now actually have the possibility to create a solar sail that would be able to travel between solar systems and go to another star. We likely couldn't travel to another star without harnessing of the energy that we already have that's given to us for free. So why not use that energy? Thank you for watching the video. I hope that you learned a lot about photon momentum like I have in creating this. Thank you for watching.